Today we are going to be discussing section 4.3. We're going to be covering polynomial division, the remainder theorem, and the factor theorem. So we're going to cover long division with polynomials. We're going to use a quicker method that's called synthetic division to divide a polynomial by a certain factor. Then we're going to talk about the remainder theorem and the factor theorem. So similar to working with numbers, whenever we have a polynomial p of x and we divide it by a polynomial d of x, we obtain a quotient and remainder, where you can take the dividend p of x, the divisor d of x, the quotient q of x, and the remainder r of x and write it in this formula. If the remainder is actually 0, then we say d of x is a factor of p of x. Now let's see an example. We're going to divide to determine whether x plus 1 and x minus 3 are factors of x cubed plus 2x squared minus 5x minus 6. So similar to our standard long division, we're going to write x cubed plus 2x squared minus 5x minus 6 under a whole big house, and we're going to put x plus 1 on the left-hand side. Now we're going to think to ourselves, what times x will give me x cubed? Just focusing in the first terms of both of these polynomials. Well, x squared times x gives me x cubed. So I'm going to write x squared right above the x squared term that's in the house. And now I'm going to think to myself, x squared times x gives me x cubed, and x squared times 1 from this plus 1 over here gives me a plus x squared. We've basically carried out the multiplication from the term we just found on top of the house, the x squared, and the x plus 1 on the left-hand side. Now we're going to subtract away that term. And notice I wrote in parentheses to make sure we subtract the whole thing. That negative needs to be distributed to the term in here. If I carry out that subtraction, I'm looking at x cubed minus x cubed, which gives me 0, and 2x squared minus x squared, which gives me a x squared. Now I drop the minus 5x. Now I think to myself, what times x gives me the x squared term now? Well, x times x gives me x squared, so I'm going to write plus x on top of the house. That keeps my x lined up with the minus 5x in the problem, in the house. Now I'm going to carry out the multiplication just between x, so this new term here, and the x plus 1 over here. Well, x times x gives me x squared, and x times 1 gives me x. I subtract the whole thing, and I get 0. Now we have minus 5x minus x, which is minus 6x. Now I'm going to drop the minus 6. So we'll only drop one term at a time. Now I think to myself, what times x plus 1 gives me a minus 6x? So minus 6. Because if I have minus 6 times x, I get a minus 6x in my first term. So we carry out the multiplication, minus 6x, and then I need to do minus 6 times the plus 1 on the left-hand side to carry out the full multiplication. And I have a minus 6 times a plus 1 gives me a minus 6. But look at that. They match perfectly, and as I take their difference, I get 0. So there's nothing left over, and I know that now I can write x cubed plus 2x squared minus 5x minus 6, I can write as x plus 1 times x squared plus x minus 6. I've basically done the division. Now let's see about x minus 3. So again, we're going to start with our polynomial under a house, x cubed plus 2x squared minus 5x minus 6. We're going to divide this by x minus 3. Starting with our first terms, we think what times x gives me x cubed? Naturally, we get x squared. We're going to carry out that multiplication between the x squared and the x minus 3. X squared times x is x cubed. X squared times minus 3 is minus 3x squared. Now I'm going to subtract this whole thing, and I get x cubed minus x cubed is 0, and then I get 2x squared plus 3x squared, which is a plus 5x squared. Notice I have to distribute that negative. So when I take the plus 2x squared in the top and I subtract the negative 3x squared, it becomes positive, and those two combine to make a plus 5x squared. So now I ask myself, what times x gives me 5x squared? And before I write that down, we're going to go ahead and drop the minus 5x. Okay, now what times 5x squared gives me? What times x gives me 5x squared? And that is a plus 5x, right? I'm comparing my first terms again, and I look, 5x times x gives me a 5x squared, and 5x times minus 3 is a minus 15x. Basically, again, carrying out the multiplication between this term and this entire term. Now I got to subtract that whole thing, and I have a 5x squared minus 5x squared gives me 0, and I have a minus 5x plus 15x gives me a plus 10x. Again, I have the minus 5x, and I have my negative being distributed, so I have a minus 5x plus 15x, which is a plus 10x overall. Now we drop our minus 6. Okay, last time. What times x gives me 10x? Well, that's clearly just 10. So I write a plus 10 at top, and then I do 10 times x minus 3. So 10 times x is 10x, and 10 times minus 3 is a minus 30. Now I subtract that whole term, and 10x minus 10x is, of course, 0, and minus 6 plus 30, because I have to distribute my negative, well, minus 6 plus 30 is a plus 24. So that means I have a remainder of 24 here, which, similar to when we do it with arithmetic, I'll just write it at the top for now. But basically this tells me I can write x cubed plus 2x squared minus 5x minus 6 as x minus 3 times x squared plus 5x plus 10 with a remainder of 24. So we just add that on. But this is what this whole process has told us. Now, to formalize that, there are a few things we want to look at. First off, let's just focus in on this formula at the bottom down here. In general, we can always do what I showed you in that last example, where we write a divisor, quotient, plus remainder. So remember, the dividend is the item under the house, the actual polynomial being divided. The divisor is the one doing the work, that's on the left-hand side of the house. The quotient is what we get on top of the house, and the remainder is what's left over. So you could almost write this d of x, house, p of x, q of x, and then plus some r of x for that remainder that gets written at the top again at the end. So some things to note are that the quotient, the thing on top of the house, must have degree less than the dividend, the thing in the house. We also must have a remainder of either 0 or have degree less than that of the divisor d of x. So essentially what's over here, what we get on that r, something left over, must have degree less than this. Essentially, you couldn't pick up another term from d of x and put it into r of x. And when we have something like in the last example, let's go back there for a second. Notice how I had 24 as my remainder. We usually don't talk about this, but this has degree 0 as a polynomial. And so this guy with degree 1 does in fact have a larger degree than the 24 that actually has degree 0. And so you'll see that a lot, where if you have you have a divisor that is a linear polynomial, so it has degree 1, then your remainder must be a constant, just a number left over, essentially. That's what that part means. Now, to check your work on your division, you can always multiply the problem back out using this formula here at the bottom. So that's super helpful because you can always check your work. You just have to multiply out each of these terms, which can be kind of long, but then add your remainder back on. Now, for the remainder theorem. The remainder theorem says if a number c is substituted for x in a polynomial f of x, then the result, which we usually call f of c, is the remainder that would be obtained by dividing f of x by x minus c. So essentially, if we can write f of x as x minus c times something plus something left over, then we know evaluating the function at f of c gives us r. So let's see that in practice. Essentially, we're going to use long division to find the quotient remainder. And we know the remainder here will be f of 2. Because notice my x minus c here, if this were x minus c, c would be 2. So we know we're thinking about this polynomial f at 2 as our remainder. Well, let's see what we get. 4x cubed minus 3x squared plus x plus 7. Draw our house, x minus 2. So now, as always, what times x gives me 4x cubed? Well, 4x squared will. And if I carry that out with all of x minus 2, I have 4x squared times x is 4x cubed. 4x squared times a minus 2 is a minus 8x squared. Oh, oops, I had a wrong exponent here. That should be 4x cubed, because 4x squared times x is 4x cubed, and 4x squared times a minus 2 is minus 8x squared. So now we subtract that whole term, and remember to distribute our negative, and we have 4x cubed minus 4x cubed is 0, and I have a minus 3x squared plus 8x squared. Well, that's a plus 5x squared. And now we drop the plus x. Okay, now we ask ourselves, what times x gives me my next first term, my newest first term, 5x squared? Well, that would be 5x, so we write that on top. Now we carry out the multiplication. Plus 5x times x minus 2. 5x times x is 5x squared. And 5x times a minus 2 is minus 10x. We subtract that whole thing. We're looking at 5x squared minus 5x squared, which is 0. And then we're looking at x plus 10x, which is a plus 11x. And now we drop the plus 7. Alrighty, last time. What times x gives us 11x? Well, 11 does. So we carry out that multiplication with x minus 2. 11 times x is 11x. And 11 times minus 2 is minus 22. We subtract that whole thing. And I have 11x minus 11x is 0. And I have plus 7 plus 22 is plus 29. So I know I have remainder 29. Well, that tells me that I can write our polynomial f of x as x minus 2 times 4x squared plus 5x plus 11 plus 29. And it also tells me that f of 2 equals 29. as in if I plugged in 2 into this polynomial f, then I would get the number 29. That's what this process tells us. Now let's see if we can't find a simpler way to do long division, because it really just came down to places where things are positioned in the polynomial and the numbers that are in the coefficients. So going off the fact that we already identified c equals 2, we're going to use that fact and the coefficients and write down a synthetic way to do division. So what we're going to write down is 4, -3, 1, and 7, which are our coefficients from the polynomial. We're going to draw 2 in this upper corner. Then we're going to leave some space for another row, and we're going to draw our bar down here. The first thing we're going to do is actually drop the 4 in the first position. And now we're going to carry out a very similar technique to before, only we're going to be adding the 2 different rows. So we get 2 times 4, which gives me 8. And that's what I write up there. So we can almost write these arrows in like a times 2. And now I'm going to add -3 and 8 to get 5. Now I'm going to do that process again where I do 2 times 5, and I'm going to write it in the next position. And I add the 2, 1, and 10 gives me 11. Now one more time, 11 times 2 gives me 22, and 7 plus 22 gives me 29. Now I'm going to draw a small bar right here, because actually 29 is what we get for our remainder in that last position. And so counting down from there, if I know it's remainder 29, then I know my polynomial went 11 plus 5x plus 4x squared, which is in fact what we got in the previous slide up here on top of the house. So this is actually just a much quicker trick way of coming up with the polynomial division. It somehow simplifies all of the procedures that we do into just adding these 2 rows and doing a bit of multiplication to come up with the next position. So it's kind of a cool trick. This again would tell us that f of 2 is 29. And it's a little bit easier than long division. So as a recap, your textbook has this really lovely diagram going on. It also describes this process, so feel free to go and check there. But to review one more time, we drop the 4. We do 4 times 2 to give us the 8. Then we add -3 and 8 to give us 5. We do another times 2 to get to 10. We add the 1 and the 10. Let me write it on the left. We add the 1 and the 10 to get to 11. Do 11 times 2 to get to 22. We add the 2 to get to 29. Add that here. So that tells us that x minus 2 times our result, which was 4x squared plus 5x plus 11. If we multiply that with x minus 2 plus 29, we get the original 4x cubed minus 3x squared plus x plus 7 as is under the house in the beginning. All right, let's practice synthetic division one more time. So to write down our numbers, we have 2, we have 7 as our coefficients. We always start there. Notice how our plus x term essentially is missing. We go right from x squared to a constant. So essentially there's a hidden plus 0x. Essentially we want to write 0 as a placeholder for our next column. And then minus 5, because placeholders matters here. So 2, 7, 0, and minus 5. And we're going to note that our c value comes from this x plus 3. Well, x plus 3 is the same as x minus negative 3. And so that tells us our c value is negative 3. So negative 3 goes in the little house up at the top. The little seat at the top, we'll say. Now I'm going to skip a line, give myself some space, and draw a bar. Now we always drop the 2 to start. And then we say 2 times negative 3. That's what gets written up here, negative 6. And now 7 plus negative 6 is 1. And we do 1 times negative 3 is negative 3. We do 0 plus negative 3 is negative 3. And now I do negative 3 times the negative 3 in the house, which is 9. I do negative 5 plus 9, which is 4. And I draw that line because I know 4 is my remainder. So I like to write that first. And I like to work my way backwards. I think it makes it easier. So R4, and the polynomial is minus 3 plus 1x. And then my x squared term, 2x squared. And then remainder 4. So that tells me 2x cubed plus 7x squared minus 5 equals x plus 3 times 2x squared plus x minus 3 plus 4 for our remainder. And I just left a note in here, make sure you always look for that missing term. If you ever see an exponent skipped, essentially, we got to fill that in with a 0. Alrighty, now we can see problems like this. Determine whether 5 is a 0 of g of x, where g of x is x to the 4 minus 26x squared plus 11x plus 25. Essentially, we want to know if g of 5 equals 0. Well, we could use the division and remainder theorem by trying to figure out if x minus 5 goes into x to the 4th minus 2x squared. You know, I could write it like this, x to the 4 minus 26x squared plus 11x plus 25. But instead of doing long division, we could do synthetic division instead. So synthetic division requires that we fill in some placeholders. Notice how our x cubed term is missing. Then we have 4, 3, 2, 1, and none, essentially in our exponents. So then our placeholders would be written out as 1, 0, 26, negative 26, 11, and 25. And we know our goal numbers to see what's happening with 5. That's our c value here. And we draw ourselves a bar to leave us some space. And now we start with our algorithm. We drop the 1. We do 1 times 5 is 5. If I add the 2, that was 1 times 5 is 5. If I add 0, remember we're always adding. Add 0 and 5, we get 5. 5 times 5 gives me 25. Negative 26 plus 25 is negative 1. Negative 1 times 5 is negative 5. 11 plus negative 5 is 6. 6 times 5 is 30. And then 25 plus 30 is 55. So we know that 55 is our remainder. And that's not 0. So 5 is not a root or a 0 of g of x. Now for the next problem, we're looking at x to the 4 plus x to the 4 minus x cubed minus 15x squared plus 40x minus 30. We're going to use synthetic division and the remainder theorem to find f of negative 4. So notice how we have perfectly descending exponents in this problem. We have an x to the 4 term, an x cubed, an x squared, an x, and a constant. So we're good to go there. Let's go ahead and start with our synthetic division algorithm. We write down all our coefficients, 1, negative 15, 40, and negative 30. And we know negative 4 is what we're looking for. Multiplying things by, essentially. And we give ourselves a line after giving ourselves space for another row. To start, we drop the 1, and then we do 1 times negative 4, which is negative 4. Negative 1 plus negative 4 is negative 5. And now we take our negative 4, again from up in the hat here. Negative 4 times negative 5 is 20. Negative 15 plus 20 is 5. Now we do 5 times negative 4, which is negative 20. 40 plus negative 20 is 20. One more time, negative 4 times 20 is negative 80. And negative 30 plus negative 80 is negative 110. And so that's our remainder, is the minus 110. And that minus 110 is our answer. F of negative 4 is minus 110. Basically what we've done is we've divided this whole polynomial by x plus 4. And we got remainder 110. And we know, based off of the remainder theorem, that that remainder is what the polynomial evaluates to. So f of negative 4 is our remainder, negative 110. This all brings us to the factor theorem, which says for a polynomial f of x, if f of c equals 0, then x minus c is a factor of f of x. This feels familiar, but it's actually an opposite direction of what we had before. So from the remainder theorem before, we note that if f of x can be written of this format, where x minus c is one of the factors, then we know f evaluated at c is our remainder. And that also tells us if the remainder is 0, so essentially it's gone, that c is actually a 0 of f of x. This tells us the opposite direction is true too. If f of c equals 0, so c is a 0 of the polynomial, then x minus c must be a factor of f of x. So f of x can be written x minus c times some q of x. Now let's try an example of this. So looking at f of x equals x cubed minus 3x squared minus 6x plus 8, we are going to try to find all of the zeros of this polynomial and see if we can factor it. So let's try some linear factors. We don't have a great starting place here, and in section 4.4 we'll actually discuss better starting places essentially for these types of problems. But for this example, let's just start with x plus 1, and let's see if that's a factor, just to try a few. Well, if I'm looking at x plus 1, then my c value, to get it of the form x minus c, my c value here is negative 1. So let's do our synthetic division with negative 1. And we write down our coefficients, 1, negative 3, negative 6, and 8. And then we leave our self-space for a row, and we write our bar. And now we drop our 1 first. And then we pull this up, and we do 1 times negative 1, which is negative 1. Negative 3 and negative 1 is negative 4. Now we take that up and say negative 4 times negative 1, and our little hat. Negative 4 times negative 1 is 4. Negative 6 and 4 is negative 2. Negative 2 and negative 1 is 2. 8 plus 2 is 10. So 10 is our remainder here. So that means that f of negative 1 is 10, which is not 0. That's not what we were hoping for. We were hoping to get 0 in our remainder. Didn't work out here. So since f of negative 1 is not 0, we know x minus 1 is not a factor. Let's try this one more time with x equals 1. Negative 1 didn't work. Maybe 1 will. Let's have c equal to 1. And we'll do it again. Let me get our polynomial coefficients, 1, negative 3, negative 6, and 8. 1, negative 3, negative 6, and 8. We give ourselves a bar. Now we're going to drop the 1 first. 1 times 1 is 1. Negative 3 plus 1 is negative 2. Negative 2 times 1 is negative 2. Negative 6 plus negative 2 is negative 8. Negative 8, I haven't been drawing my arrows. Negative 8 times 1 is negative 8. 8 plus negative 8 is 0. So here we got remainder equal to 0. That means that f of 1 equals 0, which is fantastic. We found one of our zeros. That means x minus 1 is a factor. And we also know from this algorithm that the other factor is x squared minus 2x minus 8 from right over here. So that tells us that our polynomial can be written x minus 1 times x squared minus 2x minus 8. And that's a quadratic. We can easily factor it. We have plenty of techniques for that. So x and x. What are things that multiply to 8 and add to negative 2? Well, 2 and 4 multiply to 8. So 2 and 4. And we need them to add to negative 2. They, of course, need opposite signs since they multiply to a negative 8. And then we want the negative with the larger of the two numbers, the 4. Oops. And so the plus goes with the other one. So that's what our quadratic factors to, and that tells us f of x is actually x minus 1, x minus 4, x plus 2. So there we have all of the factors of f of x. It was something that we normally couldn't have factored, but luckily x minus 1 worked out, and we only had to do synthetic division twice to find one that worked out. It brought us to a quadratic that we knew how to factor. So that can happen here, and we will, again in section 4.4, learn better choices for testing different linear factors. So you don't have to just pull out negative 1 and 1 out of thin air as testers. We'll actually have a technique for that. So for this problem, we got it all the way down to its linear terms. And of course, from this, we can pick up x equals 1, x equals 4, and x equals negative 2 as our zeros overall. And now for our last example. Here we're given a graph and we're not given the actual formula for the polynomial. We're still going to find as many factors as we can for the polynomial and construct the polynomial function with the zeros that are shown on the graph. We're going to see if it's possible to find any other polynomials with the same zeros. And then is it possible to find other polynomial functions with the given zeros and the same graph? So let's identify these zeros real quick. We have a larger graph on the next slide. Notice that our domain here goes out to 8 and goes as low as negative 8. If I count these boxes, I have 1, 2, 3, 4. I have negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. So I see zeros here, 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 and here. Which are the important places, I think. So negative 6, negative 5, 3, and 4. So that was negative 6, negative 5, 3, and 4. It's just easier to see on that larger graph. So that means our factors that we know of are x plus 6, x plus 5, x minus 3, and x minus 4. We know we have at least those 4 factors. So if we wanted to construct a polynomial with the zeros shown in the graph, we could just take that polynomial to be exactly those 4 factors: x plus 6, x plus 5, x minus 3, x minus 4. Now, if I were to plug in 0 here, this polynomial has the zeros in the graph, but if I were to plug in 0 here, I should land somewhere way up here close to 400. So this is a polynomial with the zeros in the graph, but it might not be our polynomial that represents exactly this graph shown. But it's a polynomial with the zeros, so that's fine. Now, is it possible to find other polynomial functions with the given zeros? Well, sure. What if I instead throw a 2 in front of it? 2 times x plus 6 times x plus 5 times x minus 3 times x minus 4. Sure, that's another polynomial with the same set of zeros. It's still x equals negative 6, negative 5, 3, and 4. But it's a different graph because it has the 2 out front. Now, is it possible to find any other polynomial functions with the given zeros and the same graph? Well, no. Right? We cannot have the exact same graph but have a different function, essentially. As soon as we hit those zeros and we have this specific curve going through these specific points, we are set. So the answer is no, it's not possible to find any other polynomial functions. But clearly we could find polynomials with the same zeros. They are just going to have different graphs. So the valleys and the hills might be kind of taller or smaller than what we have here, and they just cross the axis at the same place. Things like that can happen. So, as always, please reach out if you have any questions. I'll see you in the next one.